Hello, my name is Tatsuya Yatagawa from the University of Tokyo. Because the first author Takahiro has already graduated from the university, I'll make a presentation instead of him. So today, I'll present our research, real-time shading with freeform planar area lights using linearly transformed cosines. Before introducing our method, let me introduce a pioneering work for flat area light shading by Baum et al. In their method, a Lambertian surface illuminated by a polygonal area light can be efficiently evaluated by the integration shown in this slide. In this integration, the cosine function is integrated over a slit angle on the hemisphere shown in the right figure. And according to Lambert's study, the result of this integration will be the same as the area of the projected figure shown at the bottom. More elaborately, the area of the projected figure is analytic when the right shape is a polygon. In this slide, a triangle is projected on the hemisphere. For each of the three edges of a projected triangle on the hemisphere, we can define a thumb by connecting the edge with the center of the hemisphere. In fact, the area of the projected figure on the shading plane is the sum of the areas of the thumb projected further on the shading plane. Because the area of a thumb projected on the shading plane can be efficiently calculated using basic algebra, we can also efficiently evaluate the area of the projected figure using the formula shown at the bottom of this slide. After this pioneering study, several approaches have been introduced for more general rendering scenes. For example, Arbor extended the for form BRDF of glossy surfaces and Heitz et al. Did for microfacet BRDF. Another research enabled to handle several special light shapes such as ellipses and lines, and some others have extended to represent a polygonal light by clipping spherical harmonic lighting. However, despite such a number of extensions, the freeform area light has not been investigated well in real-time rendering. Therefore, our research aims to achieve real-time rendering with freeform area lights whose boundary shape is represented by the third-order Bézier curves. Our method is simple, which approximates a boundary curve with a polygon and applies Baum's method to the resulting polygon. To polygonize the boundary curve, we propose an adaptive approach that takes care of the magnitude of illumination from a part of the area light. In addition, we extend the Heitz et al.'s approach for microfacet BRDF. Their method requires a special clipping operation to obtain correct shading results. We extend the clipping operation for the boundary shape defined by a polynomial curve. So let's move on to the first part, the adaptive boundary polygonization taking care of light contributions. I guess many of you may think that calculating the area of the projected figure is not so difficult even when the boundary is a polynomial curve, so I'll show you what happens in that case. Let us define each of the x, y, and z coordinates of a point on the curve C is defined as a polynomial. Without loss of generality, we can assume the shading point is at the origin. In this case, the projection on the hemisphere can be easily defined by normalizing a vector from the origin to a point on the boundary curve C, and we can obtain the projected curve on the hemisphere denoted by tilde C. Moreover, the projected figure is on the xy plane. We can calculate the area of the projected figure simply by integrating tilde y with tilde x, which can be transformed into another integration with the curve parameter t. Finally, the integrand will be a fraction of the polynomials shown at the bottom. Unfortunately, we are unable to solve this integration analytically and have no choice but calculate the integration numerically. So we calculate the area of the projected figure numerically, but in the proposed method, we employ an adaptive boundary polygonization based on the classic Lamberт-Douglas-Peucker algorithm to reduce the computational cost. As many of you know, this algorithm is for approximating a curve with a polyline. Please see the animation in this slide. As we can see, an intermediate point on the target curve farthest from the approximated polyline is added one after another until the entire polyline is sufficiently close to the target curve. The original algorithm is based on the distance from the polyline to the curve. In contrast, our method focuses on how the illumination will be changed when a new point is added to a polyline and continues adding points until the change is sufficiently small. Let me explain the details using an illustration. Equally to the original Lamberт-Douglas-Peucker algorithm, we incrementally subdivide a part of the boundary curve. To reduce the computational cost to find the best intermediate point, we always divide a part of a curve using the midpoint. By picking the midpoint of a curve section, we can define a small triangle considered as a polygonal light. Then, we calculate the contribution of this triangular area right, and if the contribution is more than a predefined threshold, we continue subdivision. On the other hand, when the contribution is less than the threshold, we terminate the subdivision and process the next curve section in a computation stack. We can obtain an approximate polygon by repeating this process until no more curve section remains. Because we have already calculated the contributions from the triangular parts in the polygon, we do not need to calculate the contribution for the resulting polygon anymore. To perform the adaptive polygonization, we need to determine a threshold for traverse termination. To this end, we performed a simple experiment to check the computation time and rendering quality when using fixed threshold. Intuitively, when we set a small threshold, the computation time gets longer and the quality gets better. Please look at the images shown in the top row. When the roughness of the reflection surface is low, the computation time does not get longer even by setting a small threshold. In contrast, the rendering quality gets significantly worse when the threshold is not sufficiently small. Therefore, we should use a small threshold for a surface with low roughness to obtain better quality. On the other hand, when the roughness is high, the computation time gets significantly longer with a small threshold while the rendering quality does not change. Therefore, for a surface with high roughness, we can use a large threshold to reduce the computation time. This result suggests using a dynamic threshold that is proportional to the roughness. We empirically found that the threshold of 0.1 times square roughness works fine in practice. By using this dynamic threshold, we can obtain both the speed and quality for surfaces with arbitrary roughness. Now the first part is finished and I'll show you the efficient clipping operation for polynomial curves. The clipping operation is needed when using a linearly transformed cosine to approximate a microfacet BRDF. This approximation using the linearly transformed cosines was proposed by Heitz et al. In 2016. They found that the microfacet BRDF with GGX normal distribution can be well approximated by linearly transforming the cosine distribution defined on a hemisphere. In this slide, a red arrow from left to right shows the linear transformation. Suppose that a scene consists of polygonal area light and microfacet BRDF as shown in the right of this slide. In this case, by applying the inverse of the linear transformation to the polygonal shape of the light, we can simplify the shading calculation with a Lambertian surface and the inversely transformed area light because a polygon is still a polygon even after the linear transformation. As I've already explained, we can use the efficient Baum's formula for this shading calculation. However, the inverse linear transformation sometimes causes a problem. Even when the entire part of the light is over the reflection surface, the transformation can move its part to be hidden under the ground surface. Because Baum's formula assumes that the entire light area is over the shading plane, we need to exclude the hidden part, which I enclose with a green circle in this slide, before the shading calculation. Unfortunately, when we approximate a boundary curve with a polygon with many edges, the clipping operation performed for each edge one by one takes considerable computation time and prohibits real-time computation. Therefore, to avoid one-by-one intersection checking of edges, we introduce another approach that we call the algebraic clipping. Let us review a problem to find which part of the light area we need to clip. Then we find two observations shown in this slide. First, the clipping operation is equivalent to the problem of finding points of intersection between the boundary curve and the shading plane. When the z-axis corresponds to the normal direction, the z-coordinate of the point of intersection is always 0. Because the z-coordinate of a boundary curve is represented by a polynomial, we can calculate the point of intersection by solving a polynomial equation. Specifically, we will solve a cubic equation for a third-order Bézier curve. In addition, owing to the affine invariance of Bézier curves, the curve after the inverse linear transformation can be immediately obtained by transforming only the control points of the curve. Therefore, the cubic equation we need to solve can also be evaluated immediately. Because we can algebraically solve the polynomial equation whose order is less than 5, we can use an algebraic formula to obtain the solutions. The algebraic formula for the cubic equation is known as Cardano's formula, and we first tested this formula for the algebraic clipping. But we afterward found that we need only the real number solutions, and another solution introduced by Dr. Jim Breen works fast for our purpose. The part of our shader code for solving the cubic equation is shown here. is sufficiently short and with a few if and else branches and other statements. Therefore, it works efficiently on a graphics pipeline. Now let's move on to the experiment part. The experiment setup is shown here. We use the proposed method to obtain both diffuse and specular reflections on the NVIDIA GeForce 1080 graphics card. The reference images which we compare our results with are computed using Monte Carlo path tracing of Blender cycles with GPU acceleration. The first result is for a concave shape with a hole. Our method is sufficiently general that it can handle the boundary shape that is not convex and even with a hole in the middle. Moreover, as shown in this slide, our results are almost identical to those obtained by Monte Carlo path tracing. The second result is for a character-shaped light. Our method can efficiently handle auxiliary shapes as long as the shape is defined by polynomial curves. Particularly, the third-order Bézier curve is one of the most popular choices for representing the shape in graphics production. Therefore, our method, which I presented today for the third-order Bézier curves, will be helpful in practice. The last one is for textured light. Because the previous method by Heitz et al. Can handle such a textured light, our approach can also seamlessly treat it. In the next experiment, we compare the proposed method with the previous method. To apply the previous method to boundary curves, we divided the curve into n line segments by splitting the domain of the curve parameter uniformly by the same intervals. The experiment shows that our method is as fast as the case when the previous method is applied to hexagonal approximation with n equals 6. To obtain the same quality using the previous method, we needed to use n equals 30, which consumes approximately twice more time than our proposed method. But you may wonder why our method is so fast. The direct answer to this question is a better computation order of our method. In the previous method, the entire boundary curve is divided into line segments, and for each of them, both the shading computation and the clipping operation are performed. Therefore, the computational complexity is directly proportional to the number of edges of polygonal approximation. In contrast, our method clips the boundary curve at the beginning. The early clipping operation can eliminate the following computations at the part of the reflection surface that is not illuminated by the light. Therefore, it can significantly reduce the total amount of computation. Moreover, the adaptive polygonization can concentrate the computation resource on the part of the area light that affects more to the final rendering. Because of these two reasons, our method is significantly faster than the previous method directly applied to a simple polygonal approximation. Lastly, I'll show some technical limitations of our method. Actually, there are no critical limitations because of our extensions, but our method shares the same limitations with the previous method by Heitz et al. That our method is based on. First, the shading calculation for textured area light is just an approximation. It emits a blurry appearance of the light on a glossy surface using simple Gaussian filtering. Therefore, the accuracy of the computation is not really high, so the results are visually reasonable. Second, the approximation using linearly transformed cosines is not really accurate when the reflection surface is illuminated from a slight grating angle. For instance, this can cause strange illumination shown in this slide when the light is entirely hidden under the ground but near the ground surface. So, to solve these problems, we need more investigation for improving the original approach for polygonal area light and reflection surfaces with microfacet BRDF. Now, let me conclude my presentation by summarizing the contributions. In this research, we propose a new real-time shading method for area light whose boundary shape is defined by the third-order Bézier curves. The proposed method is simple and based on several previous methods, but there are two technical contributions. First, we propose an adaptive boundary curve polygonization based on the classic Ramel-Douglas-Peucker algorithm, which takes care of the light contribution from a part of the area light. Second, we propose an efficient clipping operation that we refer to as the algebraic clipping, which is needed to extend the previous method for microfacet BRDF by Heitz et al. Thanks to these contributions, our method is more efficient than a straightforward application of the previous method to a simple polygonal approximation. More importantly, the ideas introduced in this study can be extended to other types of polynomial curves, such as rational Bézier curves and B-spline curves. That's all for my presentation. Thank you for listening. Our source code is available in our GitHub, so if you are interested in this project, please visit our project page. Thank you.